Hey, hello class. I hope you're all doing well. Today we're going to be covering the graphs of exponential functions. And what about the graphs? Well, it's very simple, don't worry. Actually, we took the 4 cases, but what we're going to do right now is understand how functions move vertically, horizontally, and whether we have a stretch or a compression vertically, and yeah, that's pretty much it. Okay, so an exponential function with the following form: b is greater than 0, b is not equal to 1, has the following characteristics. It's a one-to-one function. Now, can you remind me what is a one-to-one function? Well, it's a function that doesn't share the same y value, right? So let me give you an example. Let's say this point, actually let's take this point so it's a bit more clear. Let's say this is 4, 5, let's say. In this case, this point would be -4, 5, right? These two values, well, they share the same y coordinate, which is 5, but different x values. And in this case, it's not a one-to-one function. But the easiest way to test whether a graph is a one-to-one function is to just simply draw a horizontal line. If it crosses through 2 points, that means we do not have a one-to-one function. How do I determine whether I'm dealing with a function in the first place, right? To determine whether we're dealing with a function, you do the vertical test. If it passes through only 1 point, that means you're dealing with a function. Let's have a look at this graph. Is this a function? Well, not really, because it's passing through 2 points. Anyways, this is not our topic today. Moving on. Horizontal asymptote, we've taken this. Domain, -infinity to infinity. The range would be 0 to infinity. X-intercept none. The y-intercept would be 0, 1. Increasing if b is greater than 1. Decreasing if b is less than 1. Now have a look. This is simply a graph of f of x equal to b of x, where b is greater than 1, and this is a graph where b is between 0 and 1. I'm not going to go over this anymore. We've taken 4 different cases. You can go back to the previous video. I believe we're good on this. Like, how do you graph an exponential function with 4 different cases? The first case, we have a bx. Remember, you have a which is positive and b is greater than 1. Then you have a which is positive, b is between 0 and 1. Then you have a which is negative, b is greater than 1. Then what else do we have? A which is negative, not -1, I'm sorry, negative, and b is between 0 and 1. These are the 4 different cases. I do suggest you pause the video right now and try and graph them. If you don't know how to graph them, refer back to the previous video. Anyways, moving on. Try and sketch this function. Once you sketch it, determine the domain, the range, and the asymptote. The range represents the y values, the domain represents the x coordinates, and the asymptote would be a horizontal asymptote. Anyways, moving on. Have a look at this function. You see you see f of x, which is the blue function. Now what's going on? If I add to f of x 3 units, what happens to it? Well, it simply shifts upwards 3 units. That's it. If you add to f of x 3 units, it turns into 2 to the power of x plus 3, which is a function that's shifted upwards 3 units. Now if you subtract 3 units, it simply moves downwards 3 units. It's that simple. But what happens if I add to x? Remember when we add to x, let's say I add to x 3 units. When I'm adding or subtracting from x, that means we're dealing horizontally, right? We're dealing with the x-axis. It would either move to the left or to the right. Now if I add to x, this means it will move to the left 3 units. I'm sorry that my f is basically a stick with an s, but I believe it's more convenient than writing like an f that looks like this. This would waste you time. You see how easy that is? Anyways, moving on. But if I subtract 3 from x, it moves to the right 3 units. So if you subtract from x, it moves to the right. You add to x, it moves to the left. Let's have an example. F of x equals to 2 to the power of x. F of x plus 3 is simply 2 to the power of x plus 3. F of x minus 3, it's 2 to the power of x minus 3. It's that simple. Okay. You can read this if you want. It just simply tells you what's going on. But what I want you to take from the vertical shift is if you add to g of x, f of x moves upwards, you subtract, it moves downwards. Now, this is f of x, remember, we subtract 3, moves to the right. We add 3, it moves to the left. And yeah, that's pretty much it. Now, have a look at this function. It's 2 to the power of x plus 1 minus 3. What happened in this case? Well, it was first 2 to the power of x, right? I suggest you graph this and then move it to the right or to the left, and then move it downwards or upwards, and then determine the domain, range, and asymptote. Okay, try and solve this, please. Okay, let's have a look at vertical stretch and vertical compression. Well, for a function to stretch vertically means we're multiplying the function by a value that is simply greater than, I would say greater than 1. And yeah, it's going to be an absolute value as well. So let's say we have vertical compression and we want to compress the function vertically. We're multiplying it by a value which is between 0 and 1. That's it. So let me erase this. Let's have a look at the following two graphs. It was first f of x. It was stretched vertically. It's coming closer to the y-axis. And then it was compressed vertically with the right side, which means it's now further away from the y-axis. And yeah, that's pretty much it. Okay, moving on. Okay, well, they're mentioning that it's compressed vertically by a factor of a if absolute value of a is less than 1. Well, yeah, it's going to be basically between 0 and 1. The absolute value of a is going to be between 0 and 1. So it's compressed vertically. And absolute value of a is greater than 1, which is definitely the case, where it's simply stretched vertically. Now, what else do we have? We also have, okay, a reflection. This is really, really important. So let's say we have this graph, and we want to reflect it along the x-axis. What do? We multiply the whole function by a negative, right? In this case, it would reflect about the x-axis, so it would look like this. So if the first function is f of x, this function is negative f of x. If you want to copy this down, go ahead. I'm going to erase it in 1, 2, 3. Okay. Now, what if I have a function that looks like this, and this is f of x. I want to search for f of negative x. Well, your new function would simply be this function, where you're flipping it across the y-axis. So it goes around the y-axis, if that makes sense. And it has a y-intercept of 0, 1, and a range of 0 to infinity, domain negative infinity to infinity. So, yeah, that's pretty much it. Let's see, what else do we have? Okay, yeah, so this is what I was basically trying to tell you, is that the absolute value of a is between 0 and 1, and it's compressed, stretched if the absolute value of a is greater than 0. And what else do we have? So yeah, let's have a look at this form of the function, where it horizontally shifts c units to the left, vertically d units upwards. This is a summary to everything we just took, to be honest. We have the following function, where if a is greater, absolute value of a is greater than 1, it's stretched. If it's between 0 and 1, it's compressed. And if it reflects about the x-axis, if you multiply the whole function by negative, reflects about the y-axis if you multiply only the x value by negative. And the general equation for all translations would be the following, where a would represent stretching or compression. Then we have c, which is basically shifting left and right, and d, which is moving upwards and downwards. And that is pretty much it. That's it for today's video. I hope you took your notes, and we will see you tomorrow. Okay, bye-bye.